think about this for a second. You're standing outside, maybe feeling the sun's warmth on your face, seeing the light all around you.
Yeah, pretty common experience.
Or maybe you're listening to the radio, music just coming out of thin air, seemingly.
Yeah.
Or right now, you're connected wirelessly, perhaps through Wi-Fi.
All things we take for granted, really.
Exactly. Light, heat, radio signals, Wi-Fi. They seem totally different, don't they? One lets you see, one makes you warm, others carry sound and data.
They perform such different functions in our daily lives.
They really do. They fill our world, constantly moving energy and information around. But here's the mind-blowing part, really. Fundamentally, they're all the same kind of thing.
That's right. They're all just different faces of one single phenomenon, a type of wave.
An electromagnetic wave.
Precisely.
Mm-hmm.
And these waves, they don't just travel through the air like sound. They can travel through the absolute emptiness of space.
Which is crucial, obviously, for sunlight reaching us.
Absolutely.
And that's what we're really digging into today. We're doing a deep dive into these electromagnetic waves.
Trying to get a real handle on them.
Yeah, what are they? How do they behave? We want to explore some really fascinating examples to the whole range of these waves, the electromagnetic spectrum, and then zoom in on something like the laser, all based on the insights we've gathered from the material we've been studying.
And, one of the first things that jumps out, something that really sets these waves apart, is how they travel.
You mean it's not like sound or like ripples spreading on a pond? Those need something to ripple, right?
Exactly. Those are mechanical waves. They need a medium, a substance, whether it's solid, liquid, or gas, to actually move through. There are vibrations of that substance.
Right. No air, no sound. Simple as that.
But electromagnetic waves, completely different story. They don't need a medium. They're perfectly happy traveling through a vacuum, through empty space.
Which, as you said, is why we get light and heat from the sun. It crosses millions of miles of, well, pretty much nothingness to get here.
That's the fundamental difference. And it's tied to their speed.
Ah, yes, the speed. The material we looked at really emphasizes this. They travel incredibly fast and at a constant speed. In a vacuum, at least.
A very specific constant speed. It's a universal speed limit, in fact, often denoted by the letter C.
And the value is just staggering. It's given as approximately 3 times 10 to the power of 8 meters per second.
300 million meters every single second. It's almost impossible to truly visualize.
It really is just gone. And the material hints at the deeper physics here, connecting the speed, CC, to the ratio of the electric and magnetic field strengths in the wave.
And also to these fundamental properties of space itself, its permeability and permittivity. It shows how deeply embedded this speed is in the fabric of the universe.
But it's also noted, right, that this speed isn't always c, it changes.
That's a key point. While c is the speed in a vacuum, when an electromagnetic wave enters a medium like air, water, glass, anything it interacts with the atoms and molecules there.
And that interaction slows it down.
It does. Its speed changes, and its properties can change too. Its direction might bend, which is refraction. That's why a straw looks bent in a glass of water. The light waves slow down and change direction when they go from air to water.
Okay, so they can travel through vacuum, but they interact with matter. Let's get back to the wave itself, though. What is it, fundamentally? The material gives a pretty clear description.
It does. It's not a physical wave, like water. It's described as a propagating disturbance. A disturbance made of 2 interconnected fields, an oscillating electric field and an oscillating magnetic field.
Oscillating meaning they're constantly changing, waving.
Exactly. At any point in space as the wave passes, the strength and direction of the electric field are changing, vibrating. And the magnetic field is doing the same thing, and this pattern of vibration travels outwards.
And the material, especially with the diagrams, shows a really specific relationship between these 2 fields. They're not waving in the same direction.
No, they're perpendicular to each other. If you could picture it, imagine the electric field is waving up and down along, say, the y-axis. Then the magnetic field would be waving side to side along the z-axis, at right angles to the electric field.
Got it. Up, down, and side, side.
And then the direction the wave itself travels is perpendicular to both of those. So in our example, it would travel forward along the x-axis.
So all 3, electric field direction, magnetic field direction, and direction of travel, are mutually perpendicular, like the 3 corners of a box.
Precisely. It's a 3-dimensional wave structure.
Which makes it different from, say, a sound wave traveling through air, which is more of a compression and expansion in the same direction it's moving, right?
Yeah.
A longitudinal wave.
Correct. Here, the oscillations, the electric and magnetic fields are across the direction of travel. They are transverse.
And this transverse nature leads directly to another property the material discusses: polarization.
Yes, polarization is a key characteristic of transverse waves, including electromagnetic waves. It refers specifically to the orientation of the electric field's vibration.
Right. The material explains that ordinary light, like sunlight or light from a regular bulb, is usually unpolarized. What does that mean exactly?
It means the light is actually a jumble of waves, and the electric fields in those waves are vibrating in all possible directions. Well, all directions that are perpendicular to the direction the light is traveling.
So if light is coming towards you, the electric field is vibrating up, down, side to side, diagonally, every which way in that flat plane.
Exactly, a chaotic mix of orientations. But then you can get plane polarization.
That's where it's more ordered.
Yes, plane polarized light is light where the electric field vibrations are confined to just one single plane. Imagine sending that unpolarized light through a sort of microscopic picket fence, a polarizing filter.
Okay, like slats.
Right. Only the vibrations that happen to be aligned with the gaps in the fence can get through. Everything else is blocked or absorbed. What comes at the other side is plane polarized. Its electric field is now vibrating only in that one specific direction allowed by the filter.
And the material states that this plane, the plane the electric field vibrates in, is taken as the standard definition of the plane of polarization for EM waves.
Right. And because the electric field vibration is perpendicular to the direction of travel, this confirms that EM waves are indeed transverse waves.
The material mentions you can see this effect using special polarizing filters or even some natural crystals like tourmaline.
Yes, those materials have structures that preferentially absorb or transmit light, depending on the orientation of its electric field.
Okay, so we have these transverse waves, oscillating electric and magnetic fields traveling at sea in a vacuum. Where do they actually come from? The sources seem incredibly varied.
They really are. The material covers both natural and artificial sources. On the natural side, the biggest one nearby is obviously the sun.
Our primary source of light and heat.
Absolutely, it radiates across pretty much the entire electromagnetic spectrum. And actually, any hot object radiates electromagnetic waves that glow you see from a hot stovetop burner, or the heat you feel.
That's infrared radiation, right?
Mostly infrared, yes. It's thermal radiation. But there are many artificial ways to generate them too.
Like what?
Well, electric discharge is mentioned. Think of a lightning strike. That huge, sudden release of electrical energy creates a burst of electromagnetic waves across many frequencies.
Wow, okay.
And a really fundamental method is using oscillating electric circuits. Changing electric currents, particularly in an antenna, create changing electric and magnetic fields that then propagate outwards as waves.
That's the basis of radio, isn't it? And Wi-Fi and cell phones?
Essentially, yes. That's how we generate waves for communication. The material also gets more specific listening devices like X-ray tubes.
Designed specifically to make X-rays, presumably.
Precisely. And magnetrons.
Ah, like in a microwave oven.
Exactly. Magnetrons are devices specifically designed to produce high-power microwaves, a type of electromagnetic wave.
What else?
Arc welding and carbon arcs are mentioned as sources too, and it specifically notes they produce ultraviolet or UV rays.
Okay, so high-temperature arcs produce UV.
And then, at the really high-energy end of things, the material points to nuclear processes. Nuclear reactions, like those inside a nuclear reactor, or, unfortunately, in the explosion of a nuclear bomb, release vast amounts of energy, including very high-energy electromagnetic waves called gamma rays.
So the type of source often determines the type, or at least the dominant type, of EM wave produced, its frequency and energy.
That's a good way to put it. The mechanism dictates the output.
And this huge variety of waves coming from all these different sources leads us straight into the idea of the electromagnetic spectrum.
It does. The spectrum isn't just a random collection. It's a continuous range. It's the ordering of all possible electromagnetic waves based on their frequency, or equivalently, their wavelength.
And the crucial thing to remember, which the material stresses, is that all of these waves, radio, infrared, visible light, UV, X-rays, gamma rays, they all travel at exactly the same speed in a vacuum.
The speed of light, see.
Their differences aren't in speed, but in their energy, which is tied directly to their frequency. High frequency means high energy.
And since speed is constant in a vacuum, speed, frequency x wavelength, high frequency also means short wavelength, and low frequency means long wavelength. They're inversely related.
So the spectrum is this vast continuum, but for convenience, the material divides it into several main zones or bands.
Right. It lists 6 primary zones, starting from the lowest frequency, longest wavelength end.
Sure.
Radio waves, then infrared radiation, then the little slice of visible light, followed by ultraviolet radiation, then X-rays, and finally at the highest frequency, shortest wavelength, gamma rays or Ga rays.
Okay, let's walk through these zones as they're described, starting with radio waves.
Radio waves occupy a truly enormous range of the spectrum. The frequencies are given as starting from as low as 3 Hz, that's just 3 cycles per second, all the way up to 3 terahertz, which is 3 times 10 to the 12th Hertz.
Wow, that's a huge frequency range. And the wavelengths.
Correspondingly huge.
Yeah.
From 10 to the 8th meters, 100,000 kilometers, down to about 10 to the minus 4 meters, or a tenth of a millimeter.
That longest wavelength is bigger than planets.
It is. And because this range is so incredibly vast, it's usually broken down further into smaller bands for practical reasons, like broadcasting regulations. The material lists abbreviations like ELF, extremely low frequency, VLF, very low frequency, MF, HF, VHF, UHF, EHF, THF.
All just labels for different frequency chunks within the broader radio wave category.
Exactly. Grouped according to frequency for different uses like AM radio, FM radio, TV broadcasting, radar, satellite communication, Wi-Fi. They all use specific radio wave frequency bands.
And the material makes an interesting point about radio waves in the audio frequency range. You can't actually hear them directly.
That's right. Even if a radio wave is oscillating at, say, the 1,000 hertz, which is within the range of human hearing for sound waves, the electromagnetic wave itself isn't sound. Your ears don't detect it.
So you need something to convert it.
Yes, you need a transducer, like the speaker in your radio. The radio receiver converts the electromagnetic signal into an electrical signal, and the speaker then converts that electrical signal into physical vibrations of the air, which are the sound waves we actually hear. It's a crucial conversion step.
Okay, so that's radio waves. Moving up the spectrum, what's next?
Immediately above radio waves in frequency, we get infrared radiation, often just called IR,
And its wavelength range?
given as roughly 10 to 4 meters down to 10·7 meters. So shorter than radio waves, longer than visible light.
And this is what we perceive as heat.
Largely, yes. The material describes it as the zone where heat radiation, particularly from the sun, is primarily transmitted. It's often just called heat radiation.
So when you feel warmth from a campfire, even before you see the flames clearly, that's infrared.
Absolutely. Or the heat from a radiator, or even body heat detected by thermal cameras. That's all infrared radiation being emitted by objects due to their temperature.
Okay. And then just above infrared is the part we're most familiar with visually.
Visible light. The tiny, tiny sliver of the entire electromagnetic spectrum that our eyes happen to be sensitive to.
It really is narrow, isn't it? The wavelengths are specified from about 380 nanometers for violet light.
Up to about 760 nanometers for red light. A nanometer is 10⁹ meters, so we're talking very short wavelengths compared to radio or even infrared.
And within that narrow band, all the colors we see exist.
That's right. Different wavelengths within that visible range are interpreted by our eyes and brains as different colors. The material mentions the familiar sequence: red, orange, yellow, green, blue, indigo, violet, going from longer wavelengths, lower frequency, to shorter wavelengths, higher frequency.
So color is just our perception of the frequency or wavelength of light. Amazing.
It really is. All the beauty of a sunset or a rainbow is contained within that minuscule band of the spectrum.
Okay, what lies beyond the violet end of visible light? Higher frequency still.
That would be ultraviolet radiation, or UV, frequencies just above visible violet light.
In the wavelength range.
Given as 10·7 meters, down to about 10⁹ meters. Shorter wavelengths, higher energy than visible light.
This is the stuff in sunlight that gives you a tan or a sunburn.
Exactly. It has enough energy to cause chemical reactions in skin cells. It's also used for sterilization because its energy can damage microorganisms.
Right. Moving up again in frequency.
We get to X-rays. Now we're talking significantly higher frequencies. The range is given as 3 by 10·16 hertz up to 3 by 10⁹ hertz.
Which means much shorter wavelengths.
Yes, from 10·8 meters down to 10·11 meters, roughly the size of atoms.
And these have some serious penetrating power, right?
They do. The material highlights 2 key properties. They can ionize media they pass through.
Meaning they can knock electrons off atoms.
Precisely. They have enough energy to do that. And second, they are capable of penetrating many materials, especially less dense ones.
Which is why they're used in medical imaging. They go through soft tissue but get stopped or absorbed more by denser things like bone.
That's the key application. The material also describes how they're produced by accelerating electrons to very high speeds and then slamming them into a target material, causing them to decelerate extremely rapidly. This sudden deceleration forces the electrons to radiate away energy in the form of X-ray photons.
A very energetic process for very energetic waves.
Indeed, and that brings us to the very top end of the spectrum described.
The highest frequencies, shortest wavelengths.
Gamma rays or gay rays, frequencies above 1019 hertz.
And their properties, even more potent.
Yes, the material describes them as having very high penetrating power, even more than X-rays. They can ionize matter very effectively, reaching deeper into the atom than X-rays typically do.
And their source, as mentioned earlier, is often nuclear.
Primarily, yes. The material links them to nuclear reactions, nuclear explosions, and the processes inside nuclear power plants. They can also be generated, it says, by decelerating electrons that are already in the energetic state associated with X-rays or other high-energy particle interactions. They represent the most energetic form of electromagnetic radiation in this classification.
So that's the spectrum. Radio, infrared, visible, UV, X-rays, gamma rays. A continuous family, all traveling at Cs in vacuum, but with hugely varying energies and wavelengths, leading to vastly different properties and interactions with matter.
And the material also notes, interestingly, that external electric and magnetic fields don't affect the path or properties of these electromagnetic waves themselves once they're propagating. They carry their own fields with them.
That seems important for, say, radio signals traveling long distances without being easily deflected.
It is, and it also reiterates the practical uses, particularly mentioning again how the penetrating power of X-rays and gamma rays allows scientists to use them as probes to figure out how atoms are arranged in crystals in a technique called diffraction.
Right? Using the waves to see structures far too small for visible light.
Exactly. Understanding this whole spectrum, especially the nature of light within it and how it interacts with atoms, really sets the stage perfectly for talking about a very special technology.
Lasers.
Lasers, a technology that absolutely depends on manipulating light, a specific form of electromagnetic wave.
Yeah, the word itself conjures up images of focused beams, high-tech applications, maybe even sci-fi. The material gives a little historical context, mentioning the concept perhaps emerging around 1960 with Maimon's experiment, and crediting foundational work to Townes, Shalom, Besov, and Prokhorov.
Nobel Prize-winning work, in fact. And the name itself, ASER, tells you almost everything you need to know. It's an acronym.
Right. LASER stands for
Light amplification by stimulated emission of radiation.
light amplification by stimulated emission. That last part sounds key.
It is the key. The material explicitly states that the entire principle roots in this specific process, stimulated emission.
And the result is described as a truly unusual source of light. Not like a light bulb or the sun at all.
Very different. The material describes the beam as potentially incomparably brighter than the sun, which is hard to fathom, and it lists these defining characteristics.
Okay, what are they?
It says the beam consists of photons, particles of light, that all have the same energy and wavelength.
Meaning it's pure single-color light, monochromatic.
Exactly, monochromatic. And then crucially, these identical photons are described as traveling in phase in the same direction.
In phase, meaning their waves line up, crests with crests, troughs with troughs.
Precisely. All the waves are marching perfectly in step. This property is called coherence, and they're all going in the same direction, forming a tight parallel beam.
So monochromatic, coherent, and highly directional. That's very different from sunlight, which is a mix of colors, phases all jumbled up, spreading out in all directions.
Completely different. It's this combination of properties, the purity of color, the coherence, the directionality, which allows for very high intensity that makes laser light so unique and powerful.
Okay, so how on earth do you create light like that? How do you get amplification by stimulated emission? The material walks us through the essential physics.
It boils down to how light interacts with the atoms of the material inside the laser. There are three fundamental processes described.
Three processes. What are they?
Number one is absorption. Number two is spontaneous emission. And number three, the critical one, is stimulated emission.
Okay, let's take those one by one. Absorption sounds straightforward.
It is. The material explains it simply. An atom sitting in a low-energy state, its ground state perhaps, gets hit by a photon of light. If that photon has just the right amount of energy, an amount exactly matching the difference between the atom's current low-energy state and some specific higher energy state, E-rho, the atom absorbs the photon.
And uses that energy to jump up to the higher state.
Exactly, it gets excited. The energy relationship is given as E-rho equals HF, where H is Planck's constant and F is the frequency of the photon. The photon disappears, its energy now stored in the excited atom.
Okay, that's absorption. What about spontaneous emission?
This is what happens when an atom is already in that excited, higher energy state, EOs. It doesn't usually stay there indefinitely. The material says it can, all by itself, without any external trigger, suddenly decide to drop back down to a lower energy state.
And when it drops down, it has to release that extra energy.
Yes, and it does so by emitting a photon. The energy of this emitted photon is, again, exactly equal to the energy difference between the two states, E0.
So it gives off light?
It gives off light. But
Yeah.
here's the crucial part about spontaneous emission. It's random. The photon can be emitted in any direction, and its phase, its wave alignment, is completely random relative to any other photons being emitted nearby.
So this is how a regular light bulb works. Lots of atoms getting excited by heat or electricity and then randomly emitting photons in all directions.
Pretty much, yes. That's why the light is incoherent and spreads out. Now compare that to the third process.
Stimulated emission, the heart of the laser.
Exactly. Here's this scenario. You again have an atom that's already in an excited state, E0. But before it gets a chance to spontaneously emit, it gets hit by an incoming photon.
Okay. Does it absorb this one?
No, not if the incoming photon has a very specific energy, an energy HF that exactly matches the energy difference, EO. The atom would release if it were to drop to the lower state EO.
So an incoming photon with the right energy hits an already excited atom. What happens?
This is the magic. The incoming photon doesn't get absorbed. Instead, it stimulates or induces the excited atom to immediately drop down to the lower energy state and emit its own photon.
Okay, so the atom emits a photon like in spontaneous emission.
But here's the incredible difference. The photon that the atom is stimulated to emit is an exact clone of the incoming photon that triggered it.
A clone, meaning?
Meaning, as the material describes, it has the exact same energy, and therefore frequency and wavelength. It travels in the exact same direction, and crucially, it is perfectly in phase with the incoming photon.
Wow. So one photon goes in, interacts with an excited atom, and two identical in-phase photons come out traveling together.
Precisely. That's the amplification in LASCR. One photon triggers the release of a second, identical one. If these two photons then encounter more excited atoms,
They can stimulate more emissions, making 4 identical photons, then 8, 16, a chain reaction of identical light.
exactly, a cascade of coherent monochromatic photons all traveling in the same direction. That's how you build up the intense ordered laser beam.
But for this to work, for stimulated emission to dominate, you need lots of atoms sitting around in that excited state, right? Otherwise, the incoming photons would just get absorbed by atoms in the lower state.
That is the absolute crucial requirement. Under normal conditions, at thermal equilibrium, there are always far more atoms in lower energy states than in higher energy states, so absorption naturally wins.
So you have to somehow flip that situation.
Yes, you need to create what the material calls an inverted population. It's the reverse of the normal situation. You need to engineer conditions where there are more atoms residing in the specific higher energy state, E, than in the lower energy state, that they will transition down to via stimulated emission.
More atoms ready to be stimulated than ready to absorb.
Exactly. If you achieve that, then an incoming photon is much more likely to cause a stimulated emission, adding another identical photon, than it is to be absorbed and disappear. That's how you get net amplification.
Okay, how do you create this unnatural state, this inverted population?
You have to actively pump energy into the system. The process is called optical pumping, though other pumping methods exist too. The material describes using an external energy source, the pump, to force atoms from the lower state up into the higher energy state.
Like pushing them uphill energetically.
That's a good analogy. The pump source could be a bright flash lamp or even another laser, constantly supplying energy to excite the atoms and maintain that inverted population against the natural tendency to relax back down. Figure 8.8 in the material shows this concept.
So you've got your inverted population thanks to pumping, and stimulated emission is ready to amplify the light. But how do you make it build up into a powerful directed beam? You mentioned the chain reaction.
Right. You need a way to trap the initial spontaneously emitted photons that happen to be going in the right direction and the subsequent stimulated photons, making them pass back and forth through the active medium multiple times. This is the job of the resonator cavity.
The mirrors.
Exactly. As described and shown in Figure 8.10, the active medium, the material with the inserted population, is placed between two parallel mirrors. One mirror at one end is made to be almost perfectly reflective, say 99.9% reflective.
Bouncing nearly everything back.
Right. The mirror at the other end is made partially reflective or partially transparent. Maybe it reflects 99% and lets 1% through.
Okay, so most light bounces back, but a little bit can escape.
Precisely. Now imagine a photon is spontaneously emitted by an atom right in the middle, and it happens to travel exactly along the axis toward one of the mirrors. It hits the mirror, bounces back, travels through the medium again.
And on its way, if it encounters as in the excited state,
It stimulates them to emit identical photons, also traveling along the axis. Now you have more photons traveling back towards the other mirror. They bounce off that one, come back again, stimulating even more emissions.
so the light intensity builds up dramatically with each pass back and forth.
Yes, but only for light traveling exactly parallel to the axis between the mirrors. Photons emitted at an angle will quickly hit the sides of the cavity or miss the mirrors after a bounce or two. They just get lost.
So the mirrors not only amplify the light through multiple passes, but also select for directionality, creating that tight beam.
Exactly. They create a resonant condition for light traveling along the axis. And then, that partially reflective mirror at one end serves as the output coupler.
It lets a fraction of that super intense, coherent, monochromatic, directional light leak out.
Yes, that small percentage that escapes through the partial mirror is the useful laser beam that we see and use.
It's such an elegant system, really, using fundamental quantum interactions and some clever optics. The material then gives a couple of specific examples of real lasers.
It does, illustrating these principles. First, the ruby laser.
What's that, Mater?
It's described as a solid-state laser. The active medium is a synthetic crystal of aluminum oxide, basically sapphire, but with a small amount of chromium atoms mixed in. Those chromium ions are what actually do the lasing. It's noted as being a type of three-level laser system.
3 levels. How does that work?
Okay, so the pumping is done using a bright flash tube, which emits, the material says, a band of yellow-green light. This light is absorbed by the chromium ions, pumping them from their ground state, level 1, up to a broad, higher energy band, level 3.
Okay, that's the pumping step.
From this high band, the chromium ions very quickly decay, non-radiatively, meaning without emitting light, maybe just giving off heat or vibrations down to an intermediate level, level 2. This level is special. It's called a metastable state.
Metastable meaning relatively long-lived.
Exactly. Atoms can hang out in this metastable state for a relatively long time before spontaneously decaying further. This allows the pumping process to build up a large number of atoms in level 2, while level 1, the ground state, gets depleted. Voila.
Yeah.
You have an inverted population between level 2, the upper laser level, and level 1, the lower laser level.
So the lasing transition is from that metastable level back down to the ground state.
Precisely.
Yeah.
Stimulated emission occurs between level 2 and level 1, and the photons emitted have an energy corresponding to that difference. For ruby, the material states this results in the emission of red laser light.
And the mirrors?
Often, the ends of the ruby rod itself are polished flat and parallel and coated with reflective material to form the resonant cavity.
Clever. Okay, what's the other example?
The helium-neon laser, or heme laser, this one's a gas laser.
So the active medium is a gas.
Yes, a mixture of helium gas and neon gas contained in a glass tube. The material notes it typically operates continuously, unlike the pulsed output of early ruby lasers, and produces a beam that doesn't spread out much, low divergence.
How does the pumping work in a gas? You can't use a flash lamp easily.
Right. Here, they use an electric discharge. A high voltage is applied across the gas mixture, causing an electrical current to flow through it, like in a neon sign.
And this excites the gas atoms.
It primarily excites the helium atoms first. The electrons in the discharge collide with helium atoms, bumping them up to specific excited energy states.
Okay, so helium gets excited, but I thought neon was the lasing gas.
It is. Here's the clever part. The excited energy levels in helium happen to be very close in energy to some specific excited levels in neon. So, when an excited helium atom bumps into a ground state neon atom...
You can transfer its energy over.
Exactly. Through collisions, the energy gets efficiently transferred from helium to neon, kicking the neon atoms up into those specific excited states. This process selectively populates the upper laser levels in neon, creating the necessary inverted population relative to lower neon energy levels.
So helium acts like the pumping agent for the neon.
Precisely. Helium absorbs the energy from the discharge and hands it off to neon. Then, stimulated emission occurs within the neon atoms as they transition between these specific energy levels, producing the laser light.
What color is the heme laser typically?
The most common transition produces a bright red light, very familiar from barcode scanners and alignment tools. Mirrors are placed at the ends of the gas tube to form the resonator.
So different materials, different pumping methods, but the same core principles. Inverted population and stimulated emission within a resonant cavity.
That's the essence of it.
And given these unique properties, the coherence, monochromaticity, directionality, potential for high power, it makes sense that the applications are so widespread and, frankly, amazing. The material touches on industry first.
Yes, lasers have become workhorses in manufacturing and processing. The material mentions their use across a wide range of output powers and wavelengths for tasks like drilling tiny holes, precision cutting of metals and other materials, scribing patterns, welding components together.
Especially where precision is needed.
Absolutely. And it highlights their critical role in semiconductor manufacturing. Making the tiny chips in our computers and phones requires the kind of precision only lasers can really offer for certain steps. The unique control over energy delivery, power density, specific wavelengths, and the shape of the beam makes them incredibly versatile industrial tools.
There's even a mention of a maker-marm robot, described as a combination laser cutter, 3D printer, painter, fabricator, and assembler.
Yeah, that sounds like an example of how lasers are integrated into multifunctional automated systems. It's not just a standalone tool anymore, but a key component in advanced manufacturing, enabling complex tasks based on digital designs.
And then there's medicine. The impact seems just as profound there.
If not more so, in some ways. The material describes lasers as stable oscillators, offering surgeons unprecedented precision. One of the earliest and most striking examples mentioned is treating detached retinas.
How does that work?
The retina at the back of the eye can sometimes peel away. The material says reattachment is effected by means of a low-energy ruby laser. Essentially, the focused laser beam creates tiny controlled burns that effectively spot weld the retina back onto the underlying tissue, often preventing blindness. And crucially, it can do this with minimal damage to surrounding healthy cells.
Incredible precision. What else?
Using the laser as a surgical scalpel is mentioned, particularly for delicate operations on the brain or spinal cord.
Why a laser instead of a traditional scalpel?
A key advantage highlighted is immediate cauterization. As the laser cuts tissue, the heat seals off small blood vessels instantly. This dramatically reduces bleeding, which can be a major complication in these kinds of surgeries. It allows for a cleaner, clearer surgical field.
That makes sense. Any other medical uses?
Yes, photoradiation therapy is described. This sounds like a really targeted cancer treatment.
How does it work?
It combines laser light with a special drug that is injected into the patient. This drug has the property of being preferentially absorbed or retained by cancer cells, making them sensitive to a specific wavelength of light.
So the drug flags the cancer cells?
Sort of. Then the laser, tuned to that specific wavelength, is shown onto the tumor area. The light activates the drug only where it is accumulated in the cancer cells. This activation triggers a chemical reaction that destroys the host cancer cells.
Wow, so it targets the cancer while leaving healthy tissue relatively untouched.
That's the goal. The material even mentions specific lasers used for this, like an argon laser emitting red light, or sometimes a krypton laser combined with a fluorescent dye to produce blue light, depending on the sensitizing drug being used. It shows how tunable laser properties are vital for these advanced therapies.
So from understanding these fundamental waves rippling through space, these oscillating fields,
To mapping out their entire spectrum from radio to gamma.
we arrive at this incredibly sophisticated tool, the laser, born from harnessing one specific quantum interaction, stimulated emission.
And applying it in ways that are reshaping industry and revolutionizing medicine. It's a direct line from basic physics discovery to transformative technology.
We've really traced that path today, seeing how electromagnetic waves work, how they're categorized, and how controlling one type, light, through lasing gives us tools for cutting steel, manufacturing microchips, and even healing the human eye.
It truly highlights the power that comes from understanding these fundamental principles. The laser isn't magic. It's applied quantum mechanics and electromagnetism.
It really makes you stop and think, though. We've focused on understanding these waves, the spectrum, and this one amazing application, lasers, which mostly use visible or near-visible light.
A tiny fraction of the whole spectrum.
Exactly. We perceive the universe through that tiny visible window and maybe interact with radio and infrared a bit more consciously now with technology.
But the vast majority of that spectrum, the deep infrared, the terahertz waves, most UV, X-rays, gamma rays, carry so much information and energy that's largely invisible and perhaps still underutilized.
So if mastering just the stimulated emission of visible light led to the laser and all its applications,
It definitely leaves you wondering, doesn't it? What other revolutionary tools or insights are waiting to be discovered by learning to better generate, manipulate, and detect the waves in those other, less familiar parts of the vast electromagnetic spectrum? What potential is still hidden there?